Hi, my name is Ricardo Paisotto, and today I'm going to talk about PRIME, that stands for Programming Network Modular Extensions. Recently, software-based paradigms decoupled the network software from the hardware they execute, enabling more flexible network management operation. Firstly, software-defined networking decouples the control logic from the data plane device. More recently, programmable data planes enable us to rewrite the behavior of forwarding devices using software. This motivated many emerging applications to write programs for the data plane process and analyze data, which enables faster reactions in contrast to vector mirror intermediate blocks or controller-based applications, which were a common approach for software-defined networks. However, current strategies or languages for data planning do not support modular development. For, which is one of the most popular languages for data planning, would require extensive first source code modifications for us to deploy multiple programs at the same switch device. To solve this problem, researchers have responded by offering virtualization instances. However, current strategies uses excessive number of partial states and forwarding tables, which limits throughput and increases latency. Additionally, current strategies lack for abstractions that enable a consistent stream of packets of composite programs. In this work, we aim to provide a data plane composition mechanism that enables the deployment of multiple functions written as before programs. We must enable multiple programs to share the same switch device and provide ways to steer packets consistently between the programs composed. By consistency, we mean that a packet should not see a mix of two different states when traversing a switch. Representing the figure, two switch states. On state 1, packets of flow 1 traverses program 1 and program 3. And state 2, packets of flow 1 traverses program 1 and program 2. A transition between a state to another should not enable any packet to see a mixture of these states. This means that the packet should see only state 1 or only state 2. Now, we'll provide some background on PHOR language. PHOR is a high-level data planning programming language that divides the behavior of the data plane into three main blocks: a parser, a pipeline of meta action, and a deparser. A parser state machine is a state machine where program declares names for each header field, so the parser can reference bit fields into typed data of the language to be referenced next on other blocks. Representing the figure example of a parser, which have three different states: a start state, a parse Ethernet state, and a parse IP4 state. In the parse Ethernet state, we have two possible transitions: one transition for parse IP4 and one accept transition. After being processed by parsers, the packet is processed by control flows. Control flows are composed of a set of logical meta action tables and registers. An apply block specifies the semantics and the ordering in which we process the content of header attributes. We present an example of a control block called ingress, which defines an action, defines a forwarding table, and a apply block that invokes the forwarding table declared by the program. After being processed by control flows, a packet is processed by the parser. The parser writes the values of internal variables to the packet header and emits the packet to an output port or circulates back to the parser. We present an example of the parser that emits first header Ethernet and then emits IP4 header. In this work, we propose PRIME, which is a composition mechanism that enables us to compose multiple programs into one single program to be deployed into a switch device. We also provide techniques to enable a consistent steering of packets between composite programs. The high-level architecture of PRIME enables network operators to write separate independent before program modules. We then use source code merging to compose both programs into a single program, which we call the host program, that is also provided by Prime. During the composition, we go through a source code analysis that identify conflicts between program modules, and if we pass this analysis, we may deploy this program to the switch device. After deployment, Prime provides a steering interface where network operators may specify sequences of programs that may process a packet. The steering interface translates the high-level command into entries of a new additional table, which we call the steering table, that specify in which order a packet must be processed. Now we'll describe how to compose programs. The composition begins by composing parser trees. The composition of parsers expects as input two different program parsers. The composition begins by the root of the parser, where we compose into a single state equivalent states. After composing the root of the resulting parser, we compose transitions. Equivalent transitions that have the same label are composed and merged into a single transition. Different transitions are composed equally to the new resulting parser. After composing transitions, we compose the states that are mapped for these transitions. Equivalent states are composed and merged into one single state. Another states are composed the way that they were in the composed program. Then I repeat the step that we compose transitions and then compose states. We repeat that until we have all the parser state machine. Finally, we constrain the scope of the resulting parser, requiring it to be deterministic and loop-free. To this end, we perform an in-depth search in the resulting parser. If the resulting parser have non-determinism or loops, we set a warning for the operator that must solve conflicts between state machines to deploy the program correctly. After composing parser state machines, we compose the parsers. Composing the parsers must ensure that the packets are emitted in order. To design the system should not emit IPv4 headers before emitting TCP, for example, which would impacting out of order read or writes in the next hop or in the same hop if we recirculate the packet. To avoid this kind of disruption, we perform or divide the parsing composition in two different steps. First, we unite the set of emitted headers from both programs into one single set. Now that we have all the packets of the packet headers that must be emitted, we must emit in the same order that is instantiated by the parser. For example, if the resulting parser emits first TCP and then IPv4, we will emit them in this order. After composing the parsers, we compose control flows. The composition of control flows aggregating program control flows into additional table, which we call the steering table. The composition of a new program composes the program at the beginning of the pipeline, and subsequent compositions will appear in the host program in the order. This means that programs composed appear in the source code of the host program in the order they are composed. During this composition, we perform a source code analysis to ensure that the programs are isolated, its variables are isolated. To this end, we identify equivalence of constructs such as tables, actions, and registers, ensure they do not violate table dependencies. And if we found some violation, we solve this conflict and rewrite the invocation. Beyond the contributions of composition, We also present techniques to keep consistency when we steer a packet through composite programs. The steering table plays a central role in providing consistency. The steering table intercepts every packet that enters the switch. When a packet matches the steering table, an action, which we call the catalog, will load the processing order for this packet. This processing order will be stored as packet metadata, which is per packet state, and determine the order in which programs will process this packet. After loading the packet processing order, it will be processed by the first program of the catalog. Note that any program that processes this packet will change the values of catalog. This is ensured by our source code analysis that isolates programs. After a program is processed by the first program of the catalog, it recirculates back. It also recirculates back the values of the catalog. If our language does not recirculate the metadata values automatically, so we must rewrite this. After recirculation, the steering table will not apply the packet, which will enable the potential of rewriting the catalog. Therefore, we only update what is the next program to process this packet and process this. We repeat this until every program of the catalog processes the packet. Note that this is guaranteed that any subsequent update of the steering table will impact on packet being processed, ensuring that any packet will see a intermediary state. Subsequent updates will only apply to next packets. To evaluate Prime, we create experimental setup using existing application. To perform our use cases, use firstly FlowStalker, which is a monitor mechanism that encodes metrics and stores them on data plane devices. Then we use Int, that's a framework that allows collection reporting of network state by the data plane. Then we use LetFlow, which is a load balancer that runs on switches. LetFlow picks paths at random and balances traffic based on time bursts. Finally, we use a implementation of the Paxos, traditional consensus protocol for the data plane. We compose these programs incrementally. Firstly, we compose FlowStalker with the host program. Then we compose Int into scenario 1. This means that in scenario 2 we have Int, FlowStalker, and host program. Scenario 3 is a composition of LetFlow with scenario 2. Scenario 4, 5, and 6 are compositions of the consensus mechanism, which are dividing 3 data plane programs into scenario 3, forming 3 different scenarios. Represented in the figure source code metrics for each composition. Scenario 1, we have 3 parser states in 4 forwarding tables. On the other side, scenario 6 have 7 parser states and 16 forwarding tables. These are metrics from the source code of these applications that we're composing, not from the composition mechanism. To evaluate our compositions, we aim to measure only local metrics. We do not care for end-to-end metrics. To this end, we store timestamps in the beginning and the end of the pipeline. We store these timestamps on local register to further analysis. We compose every composition into a software switch called behavior model and pass it 1,000 requests, recording timestamps. After we traverses all the requests, we process timestamps to obtain latency and throughput. Throughput reduces as we compose more modules, and this reduction occurs because the amount of computation we required by functions. Conversely, latency increases, and the reasoning is the same. As we compose more things, it takes more time for us to process packets. However, I think that is acceptable trade-off, because now I have much more functionality on data plane. We consider as related work techniques that compose four programs to achieve some task on the data plane. Hyperfor and Improvisor are hypervisors for data plane. They compose before programs control single switch. However, they use an excessive number of parser states and forwarding tables because they use emulation. This becomes a bottleneck for data plane. Forbricks is a system for multiprocessing for programs. The system provides sequential or parallel operators, but they require a new hardware to do that. Forvisor and Deja-vu is a system that provides, actually Forvisor is a system that provides testing and operators. They compose a testing version of a program with a production version of a program. And finally, Deja-vu is a programming model for data plane that enable a switch to host several programs. They provide two different operators for programming, a parallel and sequential operators. However, any of these programs focus on steering consistency. In this work, we presented Prime. It's a composition for programs. Prime hosts several functions using only one additional table and provided techniques to perform the steering of packets made consistent. Prime still has several limitations. We do not support composing programs with recirculations or submissions, and we also didn't make any real hardware compositions. Our evaluations were only simulations. We also did not allow any dynamic composition. As a future work, we aim to explore new compilation techniques and investigate global path guarantees. In this work, we only focused on local guarantees in a single switch. Finally, we aim to study replication techniques to prevent failures of switches and both the program that hosts the steering interface. Thanks.